All right, let's talk about a class of antibiotics that are the absolute heavyweights in the fight against really serious infections. I'm talking about aminoglycosides. These are drugs that are incredibly powerful, they save lives, but they also carry some major risks. That's why we're calling them the double-edged sword of modern medicine.
So here's our game plan for today. First up, we're going to meet these powerful bacterial assassins. Then we'll get into the really cool part, how they actually sabotage the enemy's factory from the inside. From there, we'll dig into that central conflict, the power versus the peril. We'll also see how bacteria are getting smarter and fighting back. And finally, we'll look at the clever strategies doctors use to get all the benefits while minimizing the risks.
Okay, so let's start at the beginning. Just what exactly are we dealing with here? Let's meet these big guns. Now, these are not the kind of antibiotics you get for a simple sore throat. They were actually discovered way back in the 1940s, and they're derived from bacteria found in soil. The key word you need to know is bactericidal. That means they don't just slow bacteria down, they actively kill them. Think of these drugs as the special forces of antibiotics, the ones you call in when the situation is really, really serious. So how do they pull it off? I mean, what makes them such effective killers? Well, their method of attack is just brilliant. It's this devious little strategy that turns the bacteria's own survival tools against itself. Here's the play-by-play. The drug slips inside the bacterial cell. Then, it latches onto a critical piece of its protein-making machinery, the ribosome. Once it's attached, it basically scrambles the instructions coming from the messenger RNA. This forces the bacteria's own factory to start pumping out junk. Just tons of faulty, useless proteins. The bacterium is literally poisoned from the inside out, which leads to its own destruction. So you see, it's not just about stopping the bacteria in its tracks. It's a full-on act of industrial sabotage. The antibiotic hijacks the very system the bacterium needs to live and forces it to build the instruments of its own demise. And that's exactly what makes them so incredibly potent. But there's a catch. This super powerful weapon has a critical weakness, an Achilles heel, if you will. To get inside the bacterial cell in the first place, these drugs need an oxygen-powered transport system. What does that mean? Well, it means they're completely useless against anaerobic bacteria, the kind that live and thrive in places without any oxygen. And that's a big reason why you can't just use them for any old infection. And this brings us right to the heart of the story, the central theme of this whole explainer, that critical trade-off between incredible power and very real peril. And it is a true dilemma. On one side, you have this weapon that can just wipe out a life-threatening infection and fast. But on the other side, that exact same weapon can cause serious and sometimes permanent collateral damage to the patient. Let's look at that power side first. I mean, when do you use these? Well, they are absolutely essential for fighting severe infections from what we call gram-negative bacteria, which have these really tough outer walls. We're talking about life-threatening stuff like sepsis. They can also be teamed up with other drugs for a powerful 1-2 punch against serious heart infections. And they're even a go-to for things like multi-drug-resistant TB and some pretty rare infections, like the plague. Okay, but now for the peril. So why are they so risky? The problem is the drug tends to build up in really high concentrations in two specific places, our kidneys and the delicate cells of our inner ear. This can lead to kidney damage, which we call nephrotoxicity. The good news is that's often reversible. But the really scary part is the ototoxicity. That's damage to your hearing and your balance, which most of the time is permanent. And as if the risk of toxicity wasn't enough to worry about, doctors also have to deal with an enemy that is constantly learning, constantly adapting. Bacteria are definitely not passive victims in this fight. So bacteria have come up with three main ways to defend themselves. First, some of them produce enzymes that are kind of like molecular scissors. They just snip and modify the antibiotic, making it totally useless. Others will actually fortify their defenses, changing their cell wall to block the drug from ever getting in, or they'll use tiny pumps to kick it right back out. And in a really clever move, some even mutate the drug's target, the ribosome itself, so the antibiotic has nowhere to even bind. So with all this, the toxicity, the resistance, how in the world do we use these powerful but dangerous drugs safely? Well, the answer is all about being smarter, using what we know about how the drug moves through the body to our advantage. Here's a key piece of the puzzle. Unlike a lot of other drugs that hitch a ride on proteins floating around in our blood, these aminoglycosides don't really do that. Less than 10% of them bind to proteins. That means they're mostly just floating free in the body's water. And understanding that one little fact is absolutely critical for figuring out a dose that works and is also safe.
And knowing this has led to a huge shift in dosing strategy. See, instead of giving smaller doses multiple times a day, the go-to method now is what's called extended interval dosing. The idea is simple. You give one single large dose. This creates a really high peak concentration in the blood that just wipes out the bacteria. Then you let the drug level fall way, way down into a trough for a long time. This gives the kidneys and inner ear a much-needed break, allowing them to clear out the drug and avoid that toxic buildup.
And this is exactly why you can't just guess the dose. It's a science. Clinicians use something called therapeutic drug monitoring. They actually take blood samples to measure the drug levels. They have to make sure that the peak gets high enough to kill the bacteria, but just as importantly, that the trough before the next dose gets low enough to be safe. It's a high-stakes, precision balancing act. When you look at the whole picture, aminoglycosides are just a masterclass in the incredible complexity of medicine. They are powerful, they are dangerous, and they are absolutely indispensable. And it all leaves us with this one crucial question. As bacteria keep getting smarter, and the risks are always there, how do we continue to wield these double-edged swords with even greater precision? Because mastering the weapons we already have might just be as important as discovering new ones.